Welcome to Pomodoro Joe for Thursday, March 23rd, 2023. Today we're looking at LeetCode problem 1319, number of operations to make network connected. It's a medium problem. There are n computers numbered from 0 to n-1 connected by Ethernet cables listed in connections, forming a network where connections index I is equal to AB represents a connection between computers A and B. Any computer can reach any other computer directly or indirectly through the network. You are given an initial computer network connections. You can extract certain cables between two directly connected computers and place them between any pair of disconnected computers to make them directly connected. Return the minimum number of times you need to do this in order for all the computers to be connected. If it is not possible, return -1. And then we have some examples. So we've got 3 connected computers and 1 that's not connected. We need to extract 1 cable to connect all the computers together. All right, now let's see down here, we've got 4 computers that are connected, 2 that are disconnected. We need to move 2 of the cables to connect these other 2 computers. All right, let's see what our constraints are. Okay, so the main thing to note here is there are no repeated connections and no 2 computers are connected by more than 1 cable. Okay, so with that, we'll put 25 minutes on the Pomodoro timer and get started. Before I jump into coding, I'll go over the process here of how we figure out the algorithm. So let's take a look at these diagrams. We've got 3 connected computers, 1 that's disconnected in the first diagram. In the second diagram, we have 4 connected computers and 2 that are disconnected and not connected to each other. Now, it's possible that these 2 computers would be connected to each other. And that looks to me like we've got 2 networks or 2 groups of computers. Now, all we need to do is make sure that we connect every group of computers or every subnetwork to every other subnetwork. So I think that'll be my approach for this problem. We'll find all of these groups of connected computers or subnetworks and then make sure that we can connect those subnetworks to each other. Now, one thing to note here too is how do we know how many cables we need? Well, it looks like for every set of 2 computers, we'll need 1 cable between them. So you can imagine if we just had a line of computers, something like if we had A and it's connected to B, and that's connected to C. So between any 2 computers, we will need 1 cable, which means that we essentially need, so for 1 computer, we'd need 0 cables. For 2 computers, we just need 1 cable. For 3 computers, we'll need 2 cables. And 4 computers, we'll need 3 cables, 5 we'll need 4. So it looks like we'll need n-1 connections. So one quick thing we could do here is just check our n and the length of our connections and see if we have enough connections to make this network work out. So that's a simple one. Actually, there's 2 simple things here we can do. We can also check to see if n is less than or equal to 1. So let's see. If n is, I'll just say less than 2. If we have fewer than 2 computers, then we can just return 0. We don't need to move any cables. There are no computers to connect. All right, then if the length of our connections, if that is less than n-1, because it's 1 fewer than the number of computers that we have, then we can return -1. We don't have enough cables to make these networks. Okay. Now that we have those base cases out of the way, let's do some rearranging of our connections to make them a little bit more usable for us. All right, let's build a graph. In our graph, we will have, let's see, our key will be a computer number, and the value will be all the connected computers. So our graph will just be a dictionary, and we'll have for every, let's say, A and B in our connections, graph at A, let's see, I guess I can make this a default dictionary. That'll help out. It's just going to be, we can make it a list or a set. I'll make it a set. All right, so we'll start our graph as a default dictionary of sets. Now, for every A-B connection in our connections, we'll set graph at A, we'll add B, and a graph at B will add A, just saying that A and B are connected. All right, now that we have a list of all our connections, or a graph of all our connections, we'll want to go through and find all of these connected groups. So we'll start at computer 0 and then find all the computers that are connected to computer 0 and put them in one group or a set. Then we'll look at computer 2, find all the ones that are connected to computer 2, computer 3, so on and so forth. And once we have all of these groups, then we can figure out how many distinct groups we have. Once we know how many distinct groups we have, that represents distinct subnets. We just need to connect those groups together. All right, so let's do that. So let's see. We'll just go for every computer in range of our computers. Let's say something like find network for. Or maybe we'll just do network for. So we'll get the network for this computer. Now, this function we haven't created yet, so we'll have to create this network for function. I don't really like the name just network for, so we'll call it network for computer. And we'll pass in some root computer. For now, I'm just going to pass. We'll get back to this in a little bit. So network for computer. All right, so we've got a network for this computer. We'll do this for every single computer. That's going to be a little bit expensive because once we've calculated the network, let's say for computer 0, if computer 1 is connected to computer 0, we're recalculating that whole network over again. So let's keep track of which computers we still need to find their networks. So let's see, let's have a need to find network. And this will just be true or false. So let's say true for. All right, so our need to find network is just going to say we still need to find the network for every computer. So essentially the index is the computer that we're looking for, and the value will be whether or not we've already found the network for that computer. So let's see, for our computer in range, for every computer, we'll just say, let's see, we'll first check, do we need to find the network? All right, so if we need to find the network for that computer, we will find that network. So once we've found this network, now we can go through and set all of the connected computers need to find network values to false because we've found their network. All right, so we found all of our computers that are connected to our starting computer, and we're setting their need to find networks to false because we've found their network already. Now we'll need to keep track of how many networks we've found so far, so let's have some other thing here. All right, so we'll have network count and we'll start it at 0. So if we found a network, then we'll say network count. So if we found a network, then we can increment our network count. And we'll then, let's see, we've gone through, we've found all of our networks. At the very end, we'll have some network count. And just as with our computers, connecting between two networks just requires one connection. So if we have one network, we don't need any additional connections. If we have two networks, we'll need one additional connection. So our result will be the network count minus 1. All right, and I think this should do it. Oh, all right, so now we need to actually define our network for a computer function. This is the last piece of the puzzle. So we'll have some network, and we'll just set it as a set. We'll initialize it as an empty set, and we'll return our network at the end. So our network for computer starts with a root computer or base computer. We'll start the network itself as an empty set, and we will return the network at the end. Now we'll need some queue. So this will store all of our computers that we're going to look through. And I'll start with our root computer. This is going to be very similar to a depth-first search. So while we still have some computers in our queue, we'll also need to keep track of which computers we've already visited. Okay, so this is very similar to a depth-first search. We will start with some queue that contains just our root computer to start with, and we'll keep track of which computers we've seen already. So while we still have some computers in our queue, we'll grab a computer out of the queue, check to see if it's been visited. If it's already been visited, we've already seen this computer, we'll just continue. Otherwise, we'll keep track of this computer by adding it to our visited list, or visited set in this case. And then for every connected computer in our graph, so we've created this graph of connections, we'll go through every computer that's connected to this computer, and we'll add it to our queue, because we'll need to process those computers. Now our network, we could actually add it to our network here, and we should add it to our network. So let's do this. Let's see, actually, I think I want to do it up here. All right, so our network for computer is very similar to a depth-first search. We'll start out with some queue with our root computer or base computer. While we still have some computers in our queue, we'll grab a computer out. If we've already seen this one, we'll just continue. If we haven't seen it, we'll make sure we add it to our visited list, and we'll add it to our network. Then for every connected computer in our graph, so we check our graph for this computer, and every connected computer will append to our queue. Now, that means we'll be adding it to our visited and to our network eventually. At the very end, our network should reflect all the computers that are connected to this root computer, either directly or indirectly, and we'll return that network. All right, this should work. Let's see how we do. Typo. Okay, it seems to work. Let's submit this and see what kind of score we get. And we do pass. Not a very good job though. We only beat 16% for runtime and 38% for memory. Let's see if we can clean this up a little bit. We only have 7 minutes. All right. Well, let's see. One thing we can do, we are just throwing things into our queue even if they've been visited. So we can check if they've visited this computer already before throwing it into the queue. All right, let's do that. That should save us a little bit. Let's try this. All right, now we're up to 31%, a little bit better. What else can we do? Let's see. We're going through every single computer in this range. It looks like a couple things that I might have missed. One is we're not setting our own need defined network to false. So let's do that. Well, one way we can do that actually is just set this to initialize with our root. I think that'll be easiest. See if this still works. All right, 33%. So only a small gain from that one. What else can we do here? Sometimes doing this like if computer invisited then continue, it might be easier to say if the computer is not invisited, then we'll do all this. Let's try that. Oh, that's actually worse. All right, undo. We could, so by popping 0, we're actually doing a breadth first search. We could try depth first search. That might be faster. Oh, that is. So now we're at 49% for runtime. So depth first search does save us a little bit here. One other thing here, we're going through every computer in this range. What if we did something else where we had an all computers set? That's just going to be a set of the range n. And now we could say, while we have computers left in our all computers, so we'll just grab one computer out of our all computers list or set, and we'll use that computer for our calculation. Do we need to find their network? If we do find a network, or when we do find a network, I should say, we can just remove those computers from the all computers. So this should basically do the same thing as our for loop, but skipping a bunch of the computers that we don't need to worry about. All right, we also don't need this need to find networks, because if it's in the all computers, by definition, we need to find the network. So we can actually get rid of this. And I guess we don't need this either. That cleans this up quite a bit. Let's see how this goes. Still works. Let's see if we can beat our last runtime score. Ah, nuts. It works, but we still only get 34% for runtime. What else can I do here? Oh, well, we're down to 1 minute left. I don't know if I can do much more. There's probably a better algorithm for this problem. I'll just leave it at that. Well, we got a 49%. That's not terrible, although I really wish we could do better than this. Maybe you can do better. All right, check this one out. Again, this is LeetCode 1319. Check it out, see if you can do better than 49%. All right, hope you had fun, hope you learned something, hope you can go out and write better code.